Hi and welcome to Profex Tutorials. In this video I'm going to explain in more detail how we can refine the crystallite size and texture if this is something we observe in our datasets. We briefly addressed these parameters in a previous episode, but I want to give some more background information so you really understand what we are doing. What I have on the screen now is a dataset of hydroxyapatite, and I can already tell that it is nanocrystalline because the peaks are broad, there is a lot of peak overlap, and all in all the resolution is much lower than what I usually get from this instrument. So the first thing I'm going to do is I'm going to create a refinement project using the Add Remove dialog. So I press the plus/minus button, I search for my phase, hydroxyapatite, which is called apatite OH, and I can pick, for example, this one, which is the hexagonal structure for hydroxyapatite. The instrument configuration I used to measure this dataset was a Panalytical Cubics instrument, and it's called Cubics ADS 10mm, which stands for Cubics Automatic Divergence Slit with an irradiated length of 10mm. So that's the one I'm going to take. Okay, and now I have my refinement control file with the Cubics instrument configuration, my structure apatite OH, and I can immediately start my refinement. As you can see, the fit looks really bad. The calculated peaks shown in green are nowhere near the shape, specifically the width of the measured peak shown in black. And this is because I am not refining any peak broadening, neither from crystallite size nor from microstrain in this case. So let's have a look at the apatite structure files and the way I refined the profile. I can open all structure files by clicking on the diamond symbol up here. And this is the apatite structure file. And the parameter B1, which is used to refine peak broadening from crystallite size, is fixed at a value of 0. And also the parameter K2, which is used to refine peak broadening from microstrain, is also fixed at a value of 0. The parameter Gewicht is set to SPR 0, which means that we are not refining any texture at the moment. So what we see here, the shape of the calculated peaks in green, the asymmetry and the width of the peaks is what the shape generated by the instrument configuration and by the radiation spectrum without any influence from the sample itself. So obviously we want to refine the broadening from the crystallite size first, and I can simply right click on the B1 parameter and select Refine Isotropically. It will change the code to an isotropic refinement and start the refinement again. Now the fit looks a little bit better. The peaks are now a bit wider, a bit closer to the measured ones. And in fact, this one does not look too bad. It's getting close to the shape of the measured one, but all the others, specifically here, are still not wide enough. The reason is that one value to describe the size of the crystals is not enough. These crystals are needles. They grow along the Z-axis, so we need to refine an anisotropic shape. In other words, we need different crystallite sizes for different crystallographic directions. The crystals are relatively long in the direction of the Z-axis and very small in the direction of the A and B axis. So to set the crystallite size to anisotropic, we go back to the structure file and we right-click on the B1 parameter again and select Refine Anisotropically. Now the code is changed to the uniso keyword and we run the refinement again. Now the refinement is starting to look really good. We can now see that the sharper peak, this is the 002 peak along the Z-axis where the crystals are relatively long. That's why the peak is less broadened than the other ones. This one is fitted very well, and also the group of peaks overlapping around here above 30 degrees is also looking pretty good. The second parameter contributing to the peak width is the K2 parameter, which is used to refine microstrain. We can try and refine it and see if we see any improvement. Let's have a look at the chi-square parameter. Now without refining K2, it is at 1.24. So we can try and refine this one isotropically first, repeat the refinement, and check chi-square if it gets any better. And now we get 1.19. And if we go to the list file, there's a little bit of microstrain refined. We can also see in the list file, the results file, that the grain size, which is actually the crystallite size, it's not particle size. The term grain size is a little bit misleading, but it describes the crystallite size, not particle size. So it was refined as 15.23 nanometers in crystallographic direction 111. But I mentioned before that one value for the crystallite size is not enough anymore if we do an anisotropic refinement. So how can we output the sizes of the crystallites in different crystallographic direction? It's fairly simple. We can go to the structure file again, and if we define a goal for the function grain size, we can add as many of them in any direction we would like. So we just, for example, add 2 more and change the first one to a direction along the A-axis, and the second one along the C-axis. So now we get the diagonal length of or size of the crystallites, the size along the A-axis, and the size along the C-axis. We could also add the B-axis, but it's probably the same as the A-axis. Now we repeat the refinement and go to the list file again, and now we will have the values along the A and the C axis, and indeed the needles, or actually it looks a bit more like a cigar. So the diameter of the cigar is 12.55 nanometers and the length is 41.9. And because the peak broadening is more severe, the smaller the crystallites get. Usually smaller values are much more accurate than larger values. So as you can see from the estimated standard deviation, the small value has a much smaller error, 10 times smaller than the larger value. And if we get towards larger sizes, for example, more than 200 nanometers, the error gets excessively large because the amount of peak broadening is very small and we are not able to determine it reliably anymore. The values for crystallite sizes are given in nanometers, and for microstrain we have to open the context help window and click on K2 and then press the F1 key, and it says it's the square of microstrain. So if we really want to have the microstrain in percent, we have to use the square root of the value given here. We can also refine microstrain anisotropically. It's the same, we just click refine anisotropically here, repeat the refinement. But usually it doesn't make sense to refine both microstrain and crystallite size anisotropically, because we are just trying to extract too much data or too much information from the data. But we can see what happens now. We get the mean value for the microstrain again as the square of the normal microstrain. But now look at the grain sizes, the crystallite sizes. It's almost not anisotropic anymore. So now we have a strong correlation between the crystallite size and the microstrain parameter. And if we refine both of them anisotropically, we don't get a reliable result anymore. So BGMN does not really know where the anisotropy comes from, if it comes from the size-related peak broadening or from the microstrain-related peak broadening. So in this case, we have to help and we have to restrict one of the parameters to isotropic. And it helps, of course, if we have some additional information, such as electron microscopy images showing us the shape and size of the crystals. And usually, specifically in case of precipitated hydroxyapatite, as this sample here, we know that the crystals grow as needles, so we know that it's the shape that is anisotropic. So I revert the microstrain parameter back to isotropic because I think that from the background information I have, that this is the right solution. And here we are back at the values more or less we got before. For the crystallite size, there is one more thing to consider. The value we get here represent the diameter of a sphere of an equivalent size. So if we go to the BGMN user manual, not the Profex user manual, but the one for BGMN, you can get it from the website. If you don't have it yet, go to the download site. And here we can get the user manual as a PDF file. And on page 32, we can see the way BGMN calculates the mean crystallite size from peak broadening. And at some point it says that the value we get is the diameter of a sphere with the same volume. If we scroll down a little bit, there's a section about comparison with microscopic measurements of the grain size. And it says if we want to compare the grain sizes we get from the refinement with a microscopy image, we have to convert the value to the mean column length. And this is 3/4 of the mean sphere diameter. So for comparison with a microscopy image, we have to multiply the value we get in Profex with a factor of 3/4. The second parameter I would like to address is texture. And even though there is probably not a lot of texture in this data set, I will still use it to demonstrate how to refine it. If we look at the difference curve down here, there is not much of a systematic difference between the observed and the calculated patterns anymore. And we can also activate the noise cursor. I go to help, show mouse and keyboard commands. You get an overview of the different cursors we can activate. And if we press the N key here on the graph, it shows the noise cursor. This arrow bar kind of cursor shows the expected amplitude of the counting noise at different intensities. So down here on the background, this is the amplitude we expect. And up here at this high intensity, this is the amplitude we expect. If we go down to the difference curve in the negative counting area and we move around, it will always use the intensity of the observed scan, so the measured scan, and show us the intensity of the noise we expect at this intensity. So if we move back and forth here, where there's only background signal, we expect very little noise, and at higher intensities around here, we expect much more noise. And as you can see, the differences we see in the difference curve is very close to the expected noise pattern. So it seems there's really not much information left that is not yet refined by our structure model. Press N again to remove the noise cursor. But still, we can try and activate texture refinement. As I mentioned in one of the previous episodes, it's refined with the Gewicht parameter, which is basically the scaling of this structure, from which we also determine the weight fraction later on. And it uses a function called symmetrized spherical harmonics, and we can determine the order of these functions. So setting the order to 0 basically means we do not refine any texture. And if we click on refine anisotropically multiple times, we can increase the order of this symmetrized spherical harmonics function in steps of 2. We are only allowed to use even numbers here. That's why it jumps to 2, 4, 6, 8, and 10. And 10 is the highest order. We cannot go beyond that. Nothing will happen if we go beyond that. To decrease in steps of 2, we can just use refine isotropically. It's not actually true isotropic and anisotropic refinement. It just means increase and decrease one step in this specific case. So we can go back. So what should we choose here? What order of symmetrized spherical harmonics should we use? It's a bit difficult to explain. I am using a schematic representation taken from this publication by Rietveld et al., showing the complexity of the different spherical harmonics models. The geometric figures we see on the screen now represent the density of lattice plane normal vectors in all 3 dimensions of space. So for example, let's assume we are looking at the 0, 0, 1 vector. If the crystal orientation is perfectly random, we expect the same number of vectors pointing in any direction of space. So the density of these vectors, represented as a surface, would be a sphere, as we can see on the top left image. If more of the 0, 0, 1 vectors are pointing upwards, for example, because the crystals have a good cleavage or grow as platelets and tend to lie flat on their 0, 0, 1 faces, the density of 0, 0, 1 vectors in vertical direction would be higher, and the density function would assume the shape of a peanut, as shown on the bottom left figure. Such a texture model with one preferred orientation can be modeled with a symmetrized spherical harmonics function of the second order. So if we switch Gewicht refinement to SPR2, we could refine a texture model with one preferred orientation. If we need a more complex model, for example, accumulation of vectors in vertical direction and also in the sample plane, in the XY plane of the sample, we would have to increase the refinement of texture, use a more complex model, for example, SPR4. And as we go up to 6th, 8th, and 10th order, we use increasingly complex models for preferred orientation. And as you can see with an SPR10 at the bottom right, we can model extremely complex orientation models. And it is questionable whether or not this has still some actual physical meaning. So if crystals grow as needles or platelets, we usually need a simple model of texture, for example, SPR2 or maybe 4. And sometimes maybe 6 makes sense, but as we go to 8th or 10th order, we can model pretty much any mismatch in intensity of the peaks as texture, and this might not be correct. So if we have an intensity mismatch for some other reason, for example for chemical substitutions, we could model it with an extremely complex texture model, and then we would have strong correlations between the refinement of substitutions and our texture model, and then we are over processing our data. So be very careful with spherical harmonics of the 8th and 10th order. If you still cannot fit your mismatches in intensity with 4th order or maybe maximum 6th order, there's probably another reason and not just texture responsible for the intensity mismatch. So back in Profex, we want to increase this Gewicht parameter from SPR0 to, first let's start with SPR2, repeat the refinement. Again, before we start, let's remember the chi-square parameter. It's now without any texture. It's 1.19. We should always make sure that we actually see an improvement by monitoring the chi-square parameter. So not really an improvement, which is no surprise because the refinement was already so good that we did not expect any major improvement by refining texture. let's just go one higher and see if we see an improvement now. No improvement at all. So it doesn't make sense to use the spherical harmonics of the 4th degree. Let's go back to 2nd degree. And while it is running, we can open a window called Peak List. It will give us a list of all the refined peaks, and it will also show us the texture factor, how much the individual peaks are amplified or reduced by texture as compared to a totally untextured refinement. So now we have all the peaks, the ones shown up here as HKL tick marks listed here with their position in angle, and so to theta angle and D value, their integrated intensity, and we can also see the texture factor here. And these values are all very close to 1, so there's basically no texture at all. You can also hold the mouse pointer on these tick marks. There will be tooltips showing similar information, also texture, so you can easily go to a specific peak and check the texture factor to verify if it's strongly amplified or not. So that's basically all we need to know about refinement of crystallite sizes, microstrain and texture. I hope you enjoyed the video. Don't forget to like, share and subscribe to the channel, and I will see you soon.